Let us take an example to illustrate the Bernoulli's equation under irrotational flow condition. Okay. So, this is a flow through a converging duct. So, let us read the example. Consider steady incompressible two dimensional flow. I think by this time we can easily understand these terms, steady incompressible and two dimensional flow through a converging duct, and that is what is shown here, a converging duct. Okay. A simple approximate velocity field for this flow is given by this velocity field. The velocity component in the x direction increases with x, okay, because it is converging, and that is given by v naught plus bx. The x component of velocity is v naught at x equal to 0, that is this point. Okay. And what about the y component of velocity? That is given by minus by, okay, and that increases in magnitude away from the center line. The center line is y equal to 0, and in terms of magnitude it increases as you go away from the center line. Okay. That is what this tells you. And in terms of direction, above the central line, b is towards the central line because y is positive, and if you come below the central line, y is negative. So, once again the direction of y component is towards the central line. Okay. That is what this shows. Okay. And where v naught is the horizontal speed at x equal to 0, okay, and that is what is denoted here. And remember, the y component of velocity is 0 at y equal to 0. So, along the central line there is no y component of velocity. As we have seen earlier, that is a symmetry line. Okay. Why is this approximate field? Why does the question say it is approximate field? Note that this equation ignores viscous effects, that is what we are discussing now, along the walls, ignores viscous effects along the walls, but is a reasonable approximation throughout the majority of the flow field. Okay. That is what we have been telling always. Whenever we say inviscid flow, what is the region of validity? First of all, high Reynolds number. Secondly, away from the wall where the net viscous stresses are negligible. Okay. That is what this question also tells you. Note that this equation ignores viscous effects along the walls, but is a reasonable approximation throughout majority of the flow field. That is why it says approximate velocity field. Okay. What is that we are asked to find out? Show that Bernoulli equation can be applied between any two points in the flow field, which means we should show that it is a irrotational flow field, and then find the expression for the pressure field. Okay. So, let us proceed. So, first objective is to show that the flow field is irrotational, which means then we can apply the Bernoulli's equation between any two points. Okay. Now, we will consider this as something like a top view, okay, something like a top view, and flows in the xy plane, and gravity acts along the z direction. And okay, now for the Bernoulli equation to be applicable between any two points, the flow field should be irrotational. Okay. We have seen that, which means that this del cross V vector, which I expressed as shown here, has to be proved to be 0. Okay. Now, because we are considering xy plane, the component which is relevant to us is this, which is divided by 2 if it represents omega dot xy. So, these terms are 0. Okay. So, we will have to show that this omega dot xy or this term, we have to show that this term is equal to 0. Okay. So, let us do that. We are given the velocity field. So, which means we can identify the x component of velocity, y component of velocity. Let us evaluate the derivative. V y is a function of y only. So, dou v y by dou x is 0. V x is a function of x only. So, dou v x by dou y is 0. Okay. And so, this term is 0, which means that del cross V is equal to 0, which means the flow is which means that the flow is irrotational, and hence Bernoulli equation can be applied between any two points in the flow field. What does it mean? You can take any point here, Bernoulli should be valid. Somewhere here should be valid. Of course, we cannot go very near the wall as per the discussion. So, if you take any point here, then Bernoulli's equation should be valid. Okay. Now, let us evaluate the pressure field. What do we mean by pressure field? How pressure varies as a function of x comma y, that is the idea. Okay. So, these are the velocity components. Okay. I also like to mention this slide is what we are going to find out is the pressure gradient in the x and y direction, almost similar to what we had done earlier for an example under application of Euler's equation. Okay. You will see why is that so. Okay. Let us start with the velocity field in the Vx and Vy direction, and now flow is inviscid and irrotational. So, we will take the Euler equation and write the components of the Euler equation, x component and the y component. Okay. Now, let us simplify the substantial derivative of Vx dVx by dt, and as I told you, this we have already done for an example under for Euler equation, to illustrate Euler equation. So, steady state, so this is 0, okay, and these two terms are not 0. Vx is not a function of y, so this is 0, and of course, here Vz is 0, and of course, Vx is not a function of z. So, only this term contributes. Substitute for Vx and the derivative of Vx with respect to x, the partial derivative, and you get V naught b plus b squared x. Now, let us simplify the term dVy by dt, steady state. So, this term is 0, and Vy is a function of only y. So, this term is 0, this term exists, and of course, Vy is not a function of z, V is 0. Now, if you substitute for Vy and the derivative of Vy with respect to partially with respect to y, you get b squared y. Okay. Also, I would like to see, let us see why this example, this steps are same as what I had done earlier. In the example which we took for illustrating Euler equation, the velocity field was given by, it was flow between two plates, and we had a porous plate here, and there the velocity field was given by Vx is equal to V naught x by h, and Vy was given by V naught into 1 minus y by h. The functional forms are different, no doubt about it, but if you look at the functional dependency, it is same. Here also Vx depends on x only, here also depends on x only, and in the previous case also Vy depended on y only, here again depended on y only. That is why these steps are analogous, almost similar to earlier case. Okay, now, let us substitute in the Euler equation and evaluate the gradients of gradients in the two directions for pressure. So, dou p by dou x is equal to rho g x, just rearranging this equation, dou p by dou x is equal to rho g x minus rho dVx by dt. We are considering gravity only in the z direction. Okay, so, g x is 0 and minus rho into dVx by dt, which I have found out here, which is u naught b plus b squared x. And then what about dou p by dou y? Rearrange this equation, and rho g y is 0, g y is 0, and then minus rho into dVy by dt, which is b squared y. Okay. So, now we evaluated the gradient of pressure in the x direction and the y direction. Okay. Now, we will proceed towards finding out the pressure field. We will carry over the pressure gradients from the previous slide. Okay. How do we proceed? What we do is start with the pressure gradient in the x direction, dou p by dou x, and then we will partially integrate it. So, when you integrate left hand side p, right hand side minus rho and then into p naught b x and then b squared x squared by 2, and now we have a constant, since it is partial integration, that can be a function of y, which we denote as f1 of y. Now, we will differentiate it. Idea is to find out that function. So, let us differentiate the expression for pressure which we found in the previous step. So, dou p by dou y is equal to, all these terms will not contribute because they are functions of only x. Now, this differentiation will become a total differential because f1 is a function of only y. That is why we have got df1 by dy on the right hand side. Now, this should be equal to the dou p by dou y which I have found out earlier. So, we are equating it to minus rho b squared y. Okay. That is why this says differentiate and equate. What is that we have done? Took the dou p by dou x term and then integrated it, we got a function, we differentiated that expression for p, and now we got a differential of the function. Okay. So, now what should we do? Integrate. Idea is to find out f1. So, let us integrate. How do you find f1? Is integral of df1 by dy and then dy. So, we will substitute for df1 by dy, which is minus rho b squared y and then dy. When you integrate, you get rho minus rho b squared y squared by 2 and then a constant. This is just a constant, our usual constant, because it is usual integration, it is not partial integration. Okay. Okay. Now, let us substitute. Now, we have found out the expression for f1, that was our objective. Of course, the constant still remains. So, let us substitute this expression for f1 in this equation. Okay. We have substituted for f1 of y by as this two expressions, one is a constant, other is a function of y, minus rho b squared y squared by 2 plus c. Okay. Now, let us do some simple rearrangement so that it looks nice. We take out minus rho by 2, then what we have is these terms 2 v naught b x plus b squared into x squared plus y squared, and then this constant c. We will have to evaluate that now, which means we need a condition, we need a value of pressure at some point. Let us say we are given the pressure at x equal to 0, y equal to 0, and the pressure is p naught. Okay. P at x equal to 0, y equal to 0 is p naught. So, if we substitute here, the first term will vanish and left hand side will be p naught. So, c is equal to p naught. So, let us substitute, and that is the pressure field, p is equal to p naught and then this term which I have already seen. So, this gives you p as a function of x comma y. Okay. Always we should know that there is no meaning for or we cannot find pressure as an absolute value for incompressible flow. It is always the difference in pressure that matters. You see, we are when we are calculating here, we calculate p minus p naught. P naught was as a given value. So, we always find difference in pressure in incompressible flow. Okay. If it is compressible flow, then of course, the absolute pressure has a meaning. In the case of incompressible flow, we always, if you want to say more formally, we always find pressure up to an arbitrary constant or arbitrary given value of pressure, and that is what is clear from here also. Even earlier example, we found out pressure gradient, we never found out pressure. So, pressure is always given, or we always find in terms of pressure difference. Okay. Now, what we will do is alternate method of finding pressure field using the Bernoulli equation. What did we do now? We took the Euler equation, found out the two pressure gradients in two directions, and then integrated, differentiated, once again integrated to find f1, found a function f1, constant c, etc., found the pressure distribution. Now, what we will do, we will straight away use the Bernoulli equation and then find the pressure field, okay, which in one way will be much simpler, because anyway Bernoulli's equation was derived from the Euler equation. Okay. So, both should be equivalent. Now, because flow field is irrotational, I can apply Bernoulli equation between any 2 points, that is the advantage here. Okay. Because if it is not irrotational, then by applying Bernoulli's equation you cannot get the pressure field, because then you will have to apply only along streamlines. Because it is irrotational and because you can apply Bernoulli's equation between any 2 points, you can get the entire pressure field. Okay. So, let us write down the Bernoulli's equation which I have derived between 2 points 1 and 2, and this particular example they are at the same level. So, the gravity term or the potential energy term cancels out. Now, what we will do is we will consider point 2 as some position x comma y. Okay. We have the flow field like this, any point is considered as x comma y, and point 1 is 0 comma 0. We had a central line, and this we will consider as point 1, this as point 2. So, we will change the nomenclature in the previous equation. Instead of P 2 I write P. So, I have P by rho, and then instead of V 2 I write as V. So, I have V squared by 2. So, remember these are functions of x comma y, and right hand side I have P naught which is a constant value, given value at x equal to 0, y equal to 0. So, I have P naught by rho. Similarly, I have instead of V 1 I denote it as V naught. So, V naught squared by 2. So, these denote 0 comma 0 condition, left hand side you have any point x comma y. Remember we are able to write this just because it is irrotational flow. Okay. So, let us rearrange this. So, P is equal to P naught plus rho into V naught squared minus V squared by 2. Okay. Let us see how do we get the, we need to express in terms of x comma y. So, let us rewrite that expression. Okay. Now, we are given the velocity field, which means we know V x as V naught plus B x, we know V y as minus B y, which means I can find out the, what does this represent? Small v represents magnitude of velocity at any point x comma y. So, how do you find out v squared, which is square of that V x squared plus V y squared. So, we substitute for V x, we substitute for V y. So, I can find out the square of the magnitude of the velocity. So, what we want on the right hand side is V naught squared minus V squared by 2. V naught squared is given to us, it is a velocity at x equal to 0, y equal to 0. We have this term which I have found out in the previous step in terms of x and y. So, let us simplify that. Let us expand the square term. So, we have V naught squared 2 V naught B x, B squared x squared, and then B squared y squared, and this V naught squared cancels out, and what we have are these terms. So, now let us substitute back here. Okay. So, P is equal to P naught, then of course, you have minus here. So, minus rho by 2 into 2 V naught B x plus B squared into x squared plus y squared. So, this way becomes much simpler. We can straight away apply the Bernoulli's equation to find out the pressure field. Okay. Of course, same expression which I obtained from the Euler equation, I would say little more that was involved, this much more simpler. So, two different ways. Okay. So, let us summarize whatever we discussed under inviscid flows. We started with the discussion on flow regimes. They tell about the characteristics of the flow in terms of a dimensionless number, namely Reynolds number, which is the ratio of the inertial forces to the viscous forces. We looked at two regimes, one at low Reynolds number, namely laminar regime, laminar flow regime, and one at high Reynolds number, namely turbulent regime. In between, of course, you can have transition. Okay. While laminar was ordered, turbulent was highly disordered. Okay. Then we discuss the Euler equation, okay, and Euler equation is applicable for inviscid flows, which means that net viscous forces are negligible, okay, and which happens at high Reynolds number away from the wall, okay. And then we derive the Bernoulli's equation, okay, which tells you that the sum of pressure, kinetic, potential energies, of course per unit mass, is a constant. We derived that starting from the steady state Euler equation, and we derived two forms of the Bernoulli's equation. One, if the flow is inviscid, the Bernoulli equation is valid along a streamline. If it is inviscid and irrotational, then the Bernoulli equation is valid along any direction.